Today I'm going to teach you about breadth first search. Breadth first search, also known as BFS, is an algorithm for searching a graph. A graph being a finite mixes of edges and vertices. Breadth in this context means wide range. With this algorithm, we're going to be searching wide first. To utilize this, we're going to use a first in, first out data structure, also known as a queue. This means the oldest items will be the first to leave. We will name our queue the frontier. This is a list of all the vertices to be visited. Vertices colored light pink are to be visited, while vertices colored red have already been visited. We will then start at a node. In this particular case, we're going to start at A and work our way through the graph. We put A into the frontier, and now we pop or dequeue the frontier. This returns A. We now look at it and add its adjacent vertices. This will be B and C with this given graph. We add those into the frontier queue. Next, we dequeue again, returning B. Now, D and E go into the queue. Note, A is also technically adjacent to B because this is a non-directed graph, meaning it can go both ways. To prevent us from going in a loop over and over again, we will create ourselves an array or a set of all previously visited vertices. This way we can check against it and make sure that we're not stuck in some sort of loop. Since we're working with a queue, you'll notice D and E are added. However, they are at the back. So our next vertex to visit will be at the front, which is C. C's only adjacent is A, so we do nothing. We now pop off D. From there, we add in F and G to the frontier. We pop off E, we'll add H and I to the frontier, and if we pause, we can kind of get a good idea about how this algorithm is working. It is searching one level of our graph at a time. It will search that entire level and then move on to the next level. So it'll continually search out wide first, rather than searching depth or some other way of traversing the graph. Returning to the graph, we can quickly finish this off by running through F, adding J, checking G, H, and I, which have no additional vertices, and then back to J, which also doesn't have any additional vertices. This so far has been something called a traversal. It's not an actual search algorithm because we don't have an objective. We have just visited every single vertex in this graph and either printed it out or stored it somewhere. We can also utilize this as a search though. Let's adjust this so it looks more like a graph and less like a tree. To utilize it as a search, let's say we start at vertex B this time, and we want to find out if there is a vertex F that exists within this graph. To do this, we need to add a simple check. Is the current vertex the one we are looking for? If it is, we'll cut out of the program and we will return true. If it's not, we'll continue searching until we reach the very end of the graph and there's nothing left, and then we'll return false. We put B into the frontier, we dequeue it, and add its adjacent vertices, A, D, and E. We start with A, adding C onto the frontier. Next, we go with D, adding F and G to the frontier. We can now go with E, adding H and I to the frontier. We can also, continuing on, we pop C. There are no adjacent vertices, so then we pop F. Our check determines that F is in the graph, and we end the algorithm. We can return true. Yes, F exists within this graph. To visualize this code, let's take a look at this Python script that can do this breadth first search. Here we have our graph represented in code, each vertex on the left with its connections on the right, essentially the other vertices that are adjacent to it on the right. Then we have our actual runtime code right here. We import a queue, and in this case, it's a double-ended queue. That means you can add and take from each side. It's an efficient standard pattern that we can then adjust for this. It is named a DEQUE, which is pronounced DEC. We start our algorithm establishing a visited set and our queue. We pass in the starting value here. This can be any vertex within the graph. We now run through the graph, popping off our starting value, which is A. We check to see if we have visited it. Since we haven't, we print it out, add it to visited, and then check to see which neighbors haven't been visited, adding them to the frontier. We now pop off B, running through the algorithm again, checking if it's been visited, printing it, adding it to visited, and then adding its adjacency to the graph. This will run through the exact same way that we ran through the previous, just through the Python code itself, printing out every single vertice from top to bottom. If we wanted to make this a search algorithm, we can do it very quickly. We can just put an if statement. If the current node equals what we're searching for, return true. Else, if we reach the very end without getting true, we'll return false. Finally, we can get a time of this search algorithm. For both traversal and search, we're going to be running with this time of O to the V plus E. And this essentially means that it's going to be, at worst, having to traverse or search through the entire graph, all of the vertices plus all of the edges. The traversal makes sense. We're trying to get through the entire graph, so it makes sense that we would have to touch every vertice and edge. The search, however, is also like this because at worst case, our item that we're trying to find is on the very outside of this graph. Therefore, we're going to have to search everything on the inside before we get there. So that makes both the traversal and the search O of V plus E, which means it's a pretty slow algorithm to actually search through a graph. Not a bad algorithm for traversing the graph, but a pretty slow algorithm for searching the graph. And that is breadth first search. If you have any questions or comments, throw them in the comment section below, and I'll see you guys next time.